the number of electrons ejected depend upon the brightness, because brightness is actually the how many photons are there in the beam. So if only two photons are there, for example, it will be very feeble, a very weak beam. So it means only two electrons, photons there, only two electrons will be ejected. So brightness is how many photons are there, those many electrons will be ejected. Kinetic energy does not depend on brightness, because one photon will eject one electron only. Because it is particle nature, it will occupy the space of that electron, and the electron which is already present in the atom will get ejected. So one photon will eject one, whatever might be the energy. So kinetic energy will not depend on the brightness. So this is something I explained, that if threshold frequency is 5.1 to 5.2 into 10 power 14 hertz, okay, as in case of potassium metal. So this is for actually potassium metal, K, this potassium. So if the frequency is slightly less than this one, okay, even 5, we have taken red. Red has 4.3 to 4.6 into 10 power 14 hertz. So in this case, no photon will be able to eject any electron. Means the energy will not be sufficient enough to replace the electron. But if it is slightly more than that, it is for the potassium, not that. This is actually yellow light. So it is slightly more than that, 5.0 into 10 power 14. This will be able to eject the electron. Diagrammatically, we can understand this is potassium metal. Photon strikes. If photon's energy E is equal to h nu is less than 5.0 into 10 to the power 14 hertz, no electron ejected. Because there is some energy required here, which is h nu naught, which is also known as threshold energy or work function. Threshold frequency
Sir,
or work function. This is the name. Yes. Yes.
सर सर मेरे को डाउट था कि सर आपने बताया कि अगर थ्रेशोल्ड एनर्जी के मतलब बराबर या स्लाइटली ज़्यादा अगर लाइट आती है तो वो इजेक्ट कर जाता है इलेक्ट्रॉन। तो सर उसमें वेलोसिटी की कब होता है जब वो स्पीड मतलब वो वेलोसिटी अटेन कर लेती है इलेक्ट्रॉन।
Hmm. Velocity. I'm coming to that. I'm coming to that. Just in 1 minute. Okay. So in this case, no electron will be ejected because the energy is less than required. So in this case, because energy h nu is less than h nu naught, no electron ejected. So first condition we talked about, h nu is less than h nu naught, means energy of electron is less than the energy required to eject the electron. This energy is known as work function. Now, in your exam, your teacher may call this energy as E naught or W naught. Okay, as per NCRT, it is W naught. But because many guides use as E naught, you may get question as E naught also. Energy here is E or W. This h nu is represented by E or W, the energy of the electron. So first case, if energy of the electron is less than required, no electron ejected. Second case is it is exactly equal to h nu. H nu is equal to h nu naught. In this case, electron will get ejected because the energy is sufficient to replace the electron. So electron will get ejected, but with zero velocity, because all the energy is used to eject the electron. It is just equal to the energy required to eject the electron. Now the third case. The third case is when h nu, the energy of the electron photon, is greater than h nu naught. In this case, particular case, h nu naught, the electron will get ejected, and the rest of the energy, whatever is the energy extra, h nu minus h nu naught, this is the extra energy. This will be imparted to electron, and electron will be ejected with speed, with some speed, because now it has the energy, extra energy, which was required to eject the electron. Okay, more than that. So this much extra energy is imparted to electron as kinetic energy. Or in other words, you say that the total energy of the electron here is equal to the energy used plus the kinetic energy, which is given to the electron. This much used. So you can say that if 10 units energy was there with the electron and 6 was required, rest 4 will be given to electron as kinetic energy.
Sir,
Yes.
excuse me, sir.
Yes, come again.
Sir, the kinetic and the extra energy are the same, sir. Sir, in this case,
Kinetic energy and
the extra energy.
yes, that extra energy is imparted to Gyanendra.
Yes, sir.
The extra energy is imparted to the electron
Yes.
as kinetic energy.
Okay.
So this is the extra energy.
So means that kinetic energy consists of the mass of that electron along with its speed at which it is ejected. In this
Yes,
case.
because kinetic energy is equal to half mv square.
Yes, sir.
So you can write it, and you will be using that in that form. And
Yes.
h nu will be equal to h nu naught plus half mv square, where m is mass of electron, v is the velocity with which it gets ejected from the surface. This is the important formula you need to remember. Now my question is, who will tell me what is this h nu called?
So the energy with which the photon strikes the material.
Right, that is the energy. What it is called?
So threshold energy.
No, threshold energy is actually
Photo.
not.
Or it is called quantum.
Good. I think who said that?
Yash Bedi.
Okay, yes, that is correct. That is actually quantum. I told you. And who gave the name quantum?
So Planck.
So
Yes, yes, again, correct. So Planck gave this name, that is, it is quantum. So remember that in questions you might get the value as given quantum. Remember, it is quantum. You will consider that as h nu.
So if we were to define quantum, then what would we define it as?
Well, what quantum Planck defined as, Planck said that the energy can be transferred or transmitted in packets, discrete packets, not in continuous energy. Those discrete packets of energy are called quanta. So that is the definition of quantum.
Okay, sir.
So please repeat the definition once.
Well, definition as per Planck is that energy can be transmitted in discrete packets only. Those discrete packets of energy are called quanta, and are given by h nu, where h is constant, Planck's constant, 6.626 into 10 power minus 34 joule second. This value you have to memorize. You will be using it. It might not be given in the questions. and nu is the frequency of the radiation. Okay. So because this quantum is E equals to h nu, if energy is higher, it means frequency is higher. Okay. And if this energy is higher, E equals to E naught plus kinetic energy. Remember, I'm writing the same formula. H nu equals to H nu naught plus half mv square. It is actually E equals to E naught plus kinetic energy, or W equals to W naught plus kinetic energy, depending on which convention you use. Mostly as per NCERT, you will get this form, but this is again very much in use. So anyone you can use. So what I want to say here, and you need to understand that if frequency of the incoming radiation, okay, this one, if frequency is higher, it means energy is higher. From this relationship, E is equal to h nu. So if frequency is higher, energy is higher. And if this energy is higher, and here we need only constant value for a particular metal E naught. So whatever is extra, that will be imparted to the electron as kinetic energy, means kinetic energy is higher. Because here you need only constant value. Understand it with example. Suppose you have here 20 units and required is 6 units, the extra will be 14 units as kinetic energy. Suppose the frequency is higher and this E value now jumps to 25, but here it is still 6 required. This one is constant. So rest will be the kinetic energy, means kinetic energy will be higher. If frequency is higher, this energy is higher, kinetic energy is higher. Okay. So if this question appears like this, you need to use these relationships and get the answer. So the question will be basically which one is inversely proportional or directly proportional, or if something is increased, what will be the impact on the other thing. So for example, in this case, if you increase the frequency, energy will be increased. First, you increase the frequency, energy will be increased. And with this relationship, kinetic energy will be increased. Okay. So in other words, kinetic energy of the ejected electron is proportional to the frequency of the electromagnetic radiation. Okay. Electromagnetic radiation higher, energy higher, kinetic energy higher. Energy of the electron higher, kinetic energy. So all these are directly proportional to one another. And this is something I have already told you, that the difference is the kinetic energy. So from that, you get the relationship h nu equals to h nu naught plus half mv square, where h is Planck's constant.
सर आप इसको h nu not क्यों कह रहे हो?
This one is h nu naught, h nu, not this value is not.
Okay, sir.
So Planck's constant, and its value is equal to 6.626 into 10 to the power minus 34 Joule second.
Excuse me, sir.
Yes.
Sir, can you please tell me the definition of threshold energy, sir? I might have mistaken it with something else, sir, because in the notes I've written the wrong thing.
Okay, Kutam, threshold energy is the energy. Threshold, first understand 2 points I am talking about. I am talking about threshold frequency
Yes,
and
sir.
threshold energy. Okay. And both are interrelated. So first understand in terms of energy. This is say potassium metal. And energy required here is say E naught. and energy of the radiation, incoming radiation, is E. The difference E minus E naught will be imparted to electron as kinetic energy. This E naught, which is the minimum energy required to eject the electron, is known as threshold energy or work function. There are two names for this one. Both are correct. Now, when we represent these energies as per Planck's rule formula, E will be equal to h nu. So there will be some frequency of this radiation, incoming radiation.
Yes, sir.
So this nu is the frequency of incoming radiation.
So nu
And
naught
then-
is threshold frequency.
No, this is not threshold frequency. Threshold is related to work function.
Okay.
This E naught will be represented as h nu naught, because this energy can be
Yes, sir.
represented
Yes.
in this form.
Yes, sir.
Here, this frequency, which corresponds to work function, is known as threshold frequency.
Yes, sir. I was actually saying about this only, sir. Sir, so then you just told us about quantum. Is it same as E naught?
No, quantum is this one, quantum is this one. Both are quantum, but depending on if we are talking about the beam, quantum is this one.
Okay, sir.
This frequency is not of this energy, is not of the beam, light beam.
Yes, sir.
Hence, not quantum of light beam.
Okay, sir. So
This
means
is-
quantum is with respect to the projected beam.
Only beam. It can be any beam.
Okay, sir.
It can be any beam, but it should be beam. But here, this is work function energy required to eject the electron. So we are not talking about beam here.
Yes, sir. It's of the metal.
Yes, it is of the metal, energy, right?
Yes,
So
sir.
energy, because energy can be represented in this form, h nu. That's why we have represented other energy also in that form, because
Yes,
that
sir.
will correspond to some frequency. This E naught will correspond to some frequency. That frequency we will call as threshold frequency. Okay.
Okay, sir.
So here we are talking about in virtual terms. This one is in real terms, that radiation will have some energy. Here we are talking about in virtual term, where we are converting E naught into h nu naught. We are just representing it in terms of frequency. If it would have been a radiation, then it would have been of this particular frequency. Is that clear?
Yes, sir.
तो सर ई नॉट की वैल्यू कांस्टेंट रहती है
For a metal, yes, if you remember, I'm going back just to show you that I showed a table to you where I said some E naught values are there, whether, or maybe,
So the E naught values will differ with the metal, right?
यस सर
yes, all metals, for example, for potassium, it will be different, for cesium, it will be different, for rubidium, it
Yes,
will be,
sir. For different metals, different E naught values.
those metals have to be of photoelectric nature. Okay. This table here, so these are the threshold values. For example, for lithium, the work function is 2.42 electron volt. Okay, 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules of energy. Both are units of energy. How to remember that? Easy way is that electron volt equals to joule. Just substitute E with its electronic charge. Charge on one electron is 1.6 into 10 power minus 19.
19 coulomb. Yes, sir.
Right? Coulombs. So just substitute E by that value. Those many joules it will be. For potassium, for example, it is 2.25 electron volt, not joule. For joules, you will have to multiply it with 1.6 into 10 power minus 19. Then you will get the correct value.
तो सर जब सबकी अलग अलग होती है तो कांस्टेंट कैसे हुई
It is constant for that particular metal because you are not changing the metal. Or when you strike a radiation on a metal, do you change this metal in between?
No, sir.
So it is constant for that particular experiment. This remains constant because you are not changing the metal.
Sir, do we have to remember this value?
No, no. Fine. So you don't need to remember these values. These values will be given. On that basis, you will be asked questions like this. For example, this one I explained that this is the value here, threshold frequency, and they will check your knowledge whether you know that or not. If frequency is less than, no electron will be ejected. If it is greater than, then electron will be ejected. Moreover, sometimes students are confused, and this is the point where they make mistakes. It is frequency I am talking about. In case of wavelength, it is opposite because both frequency and wavelength are related by nu equals to c by lambda. Means nu is inversely proportional to lambda. So if nu increases, lambda decreases. Okay, so sometimes the same question might be asked, but instead of frequency, wavelength will be given. So if wavelength is given, it will be opposite. Are you getting me what I am saying?
Yes, sir.
Yes, sir.
Okay,
No, sir.
and that's where the students make mistakes. A more intense beam of light consists of larger number of photons, means brightness is higher. Consequently, the number of electrons ejected is also larger as compared to that in an experiment in which a beam of a weaker intensity is employed. This is I am saying again and again, this is very common question. That's why I am repeating it. Brightness is proportional to the number of photons. So intensity, brightness will be higher if we have greater number of photons. Greater number of photons is striking the metal, greater number of electrons will be ejected. But with one condition, electrons will be ejected only if the frequency is greater than the threshold frequency. Otherwise, you can have millions, billions of photons striking on the metal, not even a single electron will be ejected. Electrons will be ejected only if the frequency of incident radiation is greater than threshold frequency. Okay. Now, this nature shows particle nature. The reason is that photons replace electrons as photons replace electrons. It shows particle nature because particles occupy space. That's why. In wave nature, two waves interfere, but they do not disturb each other because that nature shows the weightless, massless nature. So in wave nature, no mass will be considered. In particle nature, mass will be considered. Any question till here? Okay. Then we have a question. Calculate the energy of 1 mole of photons of radiation whose frequency is 5 into 10 power 14 hertz. This is very easy question. You know mole concept. You know the relationship to calculate the energy from frequency. Tell me the answer. Write your answer in chat box. Don't announce your answer.
So do we have to put the value of H for this?
Yes. That's why I said you have to remember the value of H.
Yes, sir.
All students should have notebook and pen when they attend the class. Just for your information, I divide students in 3 groups. Those who are very active during the class, how many answers I receive. Then second, those who are active but not too active. And third, those who are not active at all. Ariman, your figures are correct. PAR you need to include, otherwise
Sir,
it
I
seems
accidentally
that you have applied
mistyped.
correct answer.
I
Okay,
mistyped and I accidentally pressed enter.
okay, okay. Pranav, PAR is not correct. Otherwise correct. Yash Bedi correct. Lemuel, PAR is not correct. Naman, PAR is not correct. Arjun, correct answer. Arna, PAR not correct. Just think about 10 to the power 37 into 10 to the power minus 34 will be 10 to the power 3 or 10 to the power minus 3. Ariman, same thing. Pratyush, same thing. Parts not correct. Devyansh, Yash Goyal, Kavish, not correct. Pratham, yes, correct answer. Okay, Arna, now correct. Kartike, no, Kartike, Par not correct. Sanskriti, Par not correct. Naman, correct now. Shashwat, correct. Pratyush, yes, correct. Kartike, I need to check. No. Okay, first. Okay. Now it seems that you applied correct formula. Most of you have applied correct formula except one where the value is not correct, where value is different. Otherwise, it seems that most of you have applied the correct formula. The problem is only in mathematical calculation. And mathematical calculation, you know, is not maths basically, because calculations you need in other subjects, in numericals, etc. In maths, you don't do those many calculations. So apply the formula and correct powers you have to calculate. You know that for one photon, if it is just one, energy will be E equals to h nu. But because here we are talking about 1 mole, so for 1 mole, it will be E equals to nh nu for 1 mole, where n is 6.022 into 10 to the power 23. These many photons will be there. So substitute these values. H is 6.626 into 10 to the power minus 34. So when we substitute these values, for one photon, this is the energy. For 1 mole, we multiply by 6.022 into 10 to the power 23. And we get answer as 199.51 kilojoule or 1.995 into 10 to the power 5 joules per mole. This was the problem in most of the questions. It's fine, you don't give me answer in kilojoules. You can give me answer in joule, fine. But this was the problem.
Sir, we have to bring the decimal to the first place.
Come again?
सर हमें सर डेसिमल को सर स्टैंडर्ड फॉर्म में लिखना था ना इसको.
Yes, I suggest that if you represent in joules, you write in standard form. And standard form is that there should be exactly 1 digit before decimal. So after decimal, you can have 2, 3, and then 10 to the power n, something 10 power x, say. That is the standard form. But if there is no 10 to the power something, you can represent it in normal form. That is usual form.
Sir,
Yes.
sir, if we don't mention per mole and just mention joule, is it okay? So because you have mentioned your joules per mole.
Mhm. The
So,
reason
sir,
is because it is asked for 1
for
mole.
1 mole. Yes, sir.
Yes,
That is
so,
good.
so you can write energy for 1 mole here,
Yes.
and you can leave it for with kilojoule only.
Okay, sir.
That is acceptable because we
Yes.
have already written it is energy for 1 mole.
Yes, sir. In statement form, we have to write.
Yes.
Okay, sir.
Next question, and this is a very important question. It appears quite a few times, very frequently in your examination. And just you need to understand how the question is phrased and how we can use this information. We can convert this information in some usable form. A 100-watt bulb emits monochromatic light of wavelength 400 nanometer. Calculate the number of photons emitted per second by the bulb. Now, if you see no energy is given, wavelength is given, but there
So
is some interrelation here.
So we can apply the formula E equal to hc by wavelength.
Yes, that's something we can apply to use this.
Yes.
Right. Right. Now there is another relation here. The relation is we have been asked number of photons emitted per second. And we need to know the energy per second. And if you understand from physics, you know that what is nothing but energy per second.
Yes, sir.
Right. So it means
Rate of-
the energy per second is 100 joules.
Yes.
Right. 100 watt is actually
It's-
100 joules per
It is the
second.
power.
Yes. Right. So we have
Yes.
converted power to energy for 1 second, and that's what we need to calculate. So it means E is equal to 100 joules per second. In 1 second, this much energy is obtained from the monochromatic light. And lambda is given 400 nanometer. Don't forget to convert it into meter because here we have joule. It means we need to use SI units only. 400 into 10 to the power minus 9 meters. Now apply the formula. Total energy is n times energy of 1 photon. So you can write here ET. ET represents total energy. Total energy of all photons. We don't know that number. That number is asked where n is number of photons. ET is given 100 and we have to calculate H is 6.626 into 10 to the power minus 34 and nu is C by lambda. Okay, so here you can write NHC by lambda. So C is 3 into 10 to the power 8 meter per second. And
सर ये जो सर जो फॉर्मूला में h है बीच में उसका फुल फॉर्म क्या है?
Planck's constant 6.626 into 10 power minus 34. So here from here you can calculate the value of n. That will be the answer. Other way is that first you write the equation for 1 photon and then you say for n photons it will be nh nu. Both ways acceptable. Okay. So here you can calculate energy of 1 photon. H nu equals to hc by lambda. This much is energy of 1 photon. And this much is total energy. So number of photons will be total energy divided by energy of one photon. This is similar to the same formula you have used in your previous class. This is the total area. And this is the area of one tile, say A, and total area is AT. So number of tiles will be total area divided by area of one tile. Similarly here, total energy divided by energy of one photon will be equal to number of photons emitted.
Sir?
Don't put your speaker on. Switch off your speaker phone, everyone. Yes.
Sir, when you were solving this question, sir, you wrote, sir, ET, sir, T denotes total energy.
Yes.
Okay, sir. So,
Yes.
so I wanted to ask sir that if अगर हम ये जो वेवलेंथ है अगर इसको हम 400 nm ही रहने दें और 100 जूल्स को अगर हम ईवी में कन्वर्ट कर दें so सर HC की वैल्यू 1240 होगी ना सर
Yes. But
And sir,
remember
उससे-
that if the question is in watts, the values are given in watts. That is SI unit. The answer
yes sir.
should be
So sir,
SI.
as it is 100 joules, so we can convert it into EV and then
Yes, basically answer will be same. Number of photons will be same, 2.012 into 10 power 20.
I thought that the calculations will be easier.
Yeah, that depends. You can do that. Okay, answer should be same. And in
Okay.
this case, what you are saying, answer will be same. Okay.
So my answer came out to be 2000 into 10 to the power 17. So it would also be acceptable. Or-
Yes, that is almost same. Okay. That is acceptable. The error margin, for example, suppose you have 1.99 into 10 to the power something, and your answer is 2 into 10 to the power something, your answer will be correct in this case. Or your answer is 1.98, that is also correct. So this error margin is acceptable. Next question. When electromagnetic radiation of wavelength 300 nanometer falls on the surface of sodium, electrons are emitted with a kinetic energy of this much. What is the minimum energy needed to remove an electron from sodium? If you don't read the question carefully, you might make mistake. Okay. And what is that mistake I am telling you? The question says this much energy is per mole. However, question asked minimum energy needed to remove an electron, not 1 mole of electrons. So you need to be careful here. The wavelength is given lambda equals to 300 into 10 to the power minus 9 meters. Electrons are emitted with a kinetic energy 1.68 into 10 to the power 5 joules per mole. So there are two things. Either you convert this energy to per electron first, per photon or per electron, and then do all calculations, because you will, whatever you will get, the minimum energy needed to remove means what is asked, h nu is asked, E naught or W naught. It is asked what is the minimum energy needed to remove the electron. This is the threshold energy or work function. Okay. And from here, from this lambda, so I'm explaining it diagrammatically. This is sodium metal here, according to question. Incident beam lambda is given. Here E naught you have been asked. Here kinetic energy is given 1.68 into 10 to the power 5 divided by 6.022 into 10 power 23 per electron. You remember, you know why I am doing per electron here? I think that is clear now.
Yes,
So
sir, we
this-
can use it directly in the question.
Yes. Okay. But first you have to convert it to per electron. It is given for 1 mole because
Yes.
here it is for per electron, per photon. That's why. So from here, using lambda, you can get energy E as hc by lambda. H you know 6.626 into 10 power minus 34 joule second. C is 3 into 10 power 8 meter per second. Lambda 300 into 10 power minus 9 meter. You got E. Kinetic energy calculated. The only unknown in equation E equals to E naught plus kinetic energy, only unknown is this one. E naught will be E minus kinetic energy. E you have calculated from SC by lambda. And kinetic energy you have calculated 1.68 into 10 power 5 divided by 6.022 into 10 to the power 23. You will get the answer. Just go through the steps, try to understand. If any step is not clear, why we did that, let me know. But Piyush says I am not audible. Just let me know whether I am audible or not, whether it is
Sir,
clear
you
or
are
not.
Sir, you are audible.
Sir, you're audible.
Thank you. There should not be any confusion in these type of questions. These are basically basis of the questions, other questions we will be doing later on. So if that is clear, then we move to second part. The second part here is, what is the maximum wavelength that will cause a photoelectron to be emitted? Now to understand this one, why we are calling it maximum wavelength? Maximum wavelength will be actually related to minimum energy.
frequency.
Why?
Sir, because they're inversely proportional, no? So if there is minimum frequency, then there would be maximum wavelength.
Yes, okay, correct, fine. Because here, this one energy, E naught, is the minimum energy required to remove an electron, because if the energy will be greater than this one, the electron will be ejected. So this is minimum energy. Required to remove electron. And the energy is related to wavelength. By this formula, we will call it lambda naught.
Yes, sir.
Is related to E naught, and E naught and lambda naught are inversely related. It means lambda naught is inversely proportional to E naught. So if this is minimum, lambda naught will be maximum. So the second part asks you just to calculate the related wavelength, which is related to minimum energy. And E naught you have already calculated. If you have already calculated E naught, substitute that in this formula. The wavelength you obtain will be the maximum wavelength of that radiation. Any confusion here? So in first case, we calculated the energy, this much. Then we subtracted, remember here what we are talking about, H C by lambda, energy of the electron. So energy of the electron we calculated as 6.626 into 10 power minus 19. Okay. And then we are talking about this energy, 1.68 per mole think just this is something, one step I have not written here. This I have converted to joules per mole after that. Okay. Only then I can subtract. When I converted it to joules per mole, then this value is given. This is joules per mole. And I subtracted, I got the joules per mole, and then I'll divide it by 6.022 into 10 power 23 because I have to calculate for 1 mole. So whichever way you do, the answer will be same. I found it easier to convert this one first to per photon. If you convert this as per photon, this is anyway given for 1 photon, you calculate it for 1 photon, and you will get answer as 1 electron. All these questions you have to do in assignments. So try to understand what I am doing. The method you can follow yours, whether you first convert it to for 1 electron or you first calculate it for 1 mole and then afterwards you divide it by Na, Avogadro number, to get for 1 electron. So whatever way you do it, concept should be clear. Then the second part we have to calculate the maximum wavelength. Maximum wavelength will be related to minimum threshold energy. So whatever energy we have obtained, we substitute that value, and the wavelength we get will be the maximum. So here this one is in meters. We converted it into nanometers. So we divide it by 10 to the power minus 9. Now this corresponds to green light. If you see the question, I'm going back. Okay. The question doesn't ask you in which region it belongs to. This is just for your information and you need to remember, that's why I included. This region 517, in previous class I explained that you need to remember the demarcations, that some just here, if you see the region here is actually green. So here it will be around 517 will be in this region, 517 will be in green.
Sir, could you explain the first part of the question, the method you showed once again?
The one which is given in the answer here.
Yes, sir, I did not understand the method.
Okay, this method I am explaining first by diagram. Okay. This kinetic energy here is given per mole. Kinetic energy is given something for 1 mole of electrons. It is given. Okay. And here the incident wavelength is given 300 into 10 to the power minus 9 meters for 1 electron. This is of 1 electron. If you calculate the energy as h nu, this is energy of 1 photon, only 1 photon. So the method I have used in this case, which is given here, is I need to calculate total energy as nh nu for 1 mole. So this is for 1 electron. This is for 1 mole if n is 6.022 into 10 power 23. Is that clear up to here or not? Energy for 1 electron h nu, energy for 1 mole of electron will be h nu multiplied by 6.022 into 10 power 23 because that is 1 mole, 6.022 into 10 power 23. Is that clear or not?
Yes.
Okay. So we have energy here for 1 mole and here also we have 1 mole. So now this energy E naught I can calculate. E naught will be ET minus kinetic energy, and whatever I will get, that will be per mole. Clear? So here you will substitute these values, 6.022 into 6.626 into 10 power minus 34 into nu will be C by lambda. Say HC by lambda, NHC by lambda. So
Sir, it
substitute
has to
all
be
these values.
multiplied with Na as well, no?
So
In
that
this.
is Na here. N is actually Na. This
Okay,
is
sir.
Na.
Okay.
Okay. This is Na for 1 mole. So this is for 1 mole. The kinetic energy is already given 1 mole. So you apply the formula E equals to E naught plus kinetic energy. All should be in 1 mole. Here E is ET. E naught will be ET minus kinetic energy from this formula. ET, you substitute the values Na Hc by lambda, kinetic energy per mole is given 1.68 into 10 power 5.
So,
So
sir,
from here,
instead of
whatever E
finding,
naught you will get, that will be per mole.
so sir, instead of finding the kinetic energy for one electron, you converted the total energy for to energy
1
per
mole.
mole.
Yes. Now,
Okay.
because you got this energy per mole, E naught, but question asks for 1 electron, you divide it by 6.022 into 10 power 23.
Yes,
Is that clear? Okay. So that's why if you see here, it was divided by Na. So this energy you got for 1 mole, E naught, and you divided it by Na, you got for 1 electron. Is that clear now?
तो सर हम जैसे इसको मतलब हम क्वेश्चन की स्टार्टिंग में भी कर सकते हैं या एंड में भी कर सकते हैं इसको डिवाइड मोल से इलेक्ट्रॉन में लाने के लिए.
Yes, Faizan, that's what I am saying, correct. So it's up to you which method you follow, whether you prefer to do calculations in moles first and then convert in 1 electron, or you first convert the energies for 1 electron and get the answer directly. In both cases, answer will be same. So second part should also be clear now. You need to just calculate the corresponding wavelength. Corresponding wavelength will be maximum wavelength. E naught equals to Hc by lambda naught. You will use whatever lambda naught you have will be maximum wavelength. Any confusion till here now?
No, sir.
Next question. The threshold frequency nu naught for a metal is given. Calculate the kinetic energy of an electron emitted when radiation of frequency this much is incident on the metal. So just I am giving you diagrammatic representation. You have to solve it yourself. Nu is given 1 into 10 to the power 15 hertz. Here the frequency nu naught is given 7 into 10 to the power 14 hertz. Kinetic energy is asked. So you know H nu equals to H nu naught plus kinetic energy. Hence kinetic energy will be H nu minus H nu naught, that is H nu minus nu naught. So kinetic energy will be H 6.626 into 10 to the power minus 34 nu minus nu naught. You know the values, 1 into 10 power 15 minus 7 into 10 power 14. So 10 minus, it will be 3 into 10 to the power 14. That will be the answer. This is value of nu minus nu naught. Okay. Why? Because I have converted this to 10 into 10 power 14. So 10 into 10 power 14 minus 7 into 10 power 14 will be 3 into 10 power 14. Easy question. You need to do it in assignment. So I'm skipping. Now Bohr's model for hydrogen atom. Important from the point of view of the theoretical questions and also numerical questions. Numerical questions are very easy, just formula based. You just need to understand which particular orbit we are talking about, whether it is from lower orbit to higher orbit or higher orbit to lower orbit, the transition. Okay, so that you can have the correct sign of the energy. That is where the mistakes are made. Otherwise, this concept is very easy. Bohr's model for hydrogen atom is based on some postulates given by Bohr. He said that the electrons in the hydrogen atom can move around the nucleus in a circular path. That is, circles of fixed radius. And because it is fixed radius, their energy is fixed. It is not changing. These paths are called orbits. Orbit term was earlier given by Rutherford. So it is not that Bohr said this is orbit. Orbit term was given by Rutherford, or stationary states or allowed energy states. Why stationary state? Because the energy is constant. Energy of an electron in a particular orbit is constant as per Bohr's model. These orbits are arranged concentrically around the nucleus. When we say concentrically means the center is same. This center is same concentrically. All the orbits are arranged in this way. The energy of an electron in the orbit does not change with time, means it remains same. That's why we call it a stationary state. However, the electron will move from a lower energy state to higher energy state when required amount of energy is absorbed by the electron, or energy is emitted when electron moves from higher stationary state to lower stationary state. What it means? It means that suppose this is the first orbit, second orbit, third orbit. An electron is in first orbit. Because the energy states, this is n equals to 1, n equals to 2, n equals to 3. N is the orbit number, orbit 1, orbit 2, orbit 3. So if an electron is in first orbit, it means it will have some constant energy. As per Bohr, it will possess some fixed energy. And electron in second orbit will have some fixed energy. That amount will be different. Some fixed energy here also. Energy will be constant in of electrons in second orbit and so on. It means there will be a fixed difference between the energies of two orbits. If this one is E1, this one is E2, delta E, that is E2 minus E1, will be fixed. It means if I want to move an electron from first orbit to second orbit, I will have to provide this much energy. If energy is less than this one, the electron will not move from lower orbit to higher orbit. I need to provide either this much energy or slightly greater than this energy to move the electron from lower orbit, first orbit, to second orbit. Similarly, if I want to move the electron from first orbit to third orbit, say, I will have to provide the energy equals to E3 minus E1. Again, fixed amount of energy. It is different amount, but fixed amount between two orbits. So that is what is written. And if an electron moves from higher orbit to lower orbit, the same amount of energy will be released. Now delta E energy is released. In this case, delta E energy is absorbed by the electron. So we are talking about Bohr's model. What Bohr said? Bohr said that if an electron moves from lower orbit, lower energy state, lower stationary state, all same thing, orbit, energy state, okay, all same thing. So lower stationary state, lower orbit, lower energy state to higher energy state, energy will be given to the electron. Electron will absorb energy. and will move to higher energy state if sufficient amount of energy is provided. If it is other way around, from higher energy state to lower energy state, the same amount of energy will be released from the atom by that electron, hence from the atom.
सर
Yes.
सर जैसे 1 से 2 में जाने के लिए एनर्जी मतलब रिक्वायर है, तो हमने माइनस किया 2 एनर्जी 2 माइनस एनर्जी 1, और अगर 2 से 1 में आना है तो
Even then it will be that one, but you know, because it will be always final minus initial, it will be E1 minus E2. So
सर
sign,
उस
sign
केस में
of the
उल्टा हो
energy will
जाएगा.
change, magnitude will remain same.
Means sir, it is minus when we go to high to low and plus when we go from low to high.
Yes. Okay.
Okay, sir.
Energy convention I am going to discuss. I'm just in few minutes, maybe today or in next session. Let me see the time. Okay. I will be talking about the convention of sign and why in this case, in case of atomic energies, okay, energy of electrons, we have negative energy. The sign of the energy is negative. Okay. So I'll talk about that, why this is considered as negative. Otherwise, in real world, if you say that this object has this much energy, you will always say that it is positive energy. But inside atom, we say that energy of this particular electron is negative, and energies of particular electrons are always negative inside electrons, inside atom. Their difference can be positive and negative, but the energy of the electron inside an atom is always negative. Why it is so, I will be talking about later, okay, in few minutes. So as shown here, you can see that if electron goes from lower orbit to higher orbit, it absorbs energy. Means energy is given to the electron. If it moves from higher to lower, it emits energy, means energy is released from the atom. Now, when atoms move from one energy state, so electrons move from one energy state to another energy state. This diagram I am talking about hydrogen spectrum specifically. Okay. When we are moving from higher energy state to lower energy state, there can be multiple ways the electron can move. So electron can move to first orbit from second orbit, that is this particular line shown, or it can move from third orbit directly to first orbit, or from fourth, from any orbit it can move to first. Similarly, if it moves to n equals to 2, it can move from any, from 3, from 4, from 5, from 6, whatever orbit, higher orbit, it can move to second, and so on. Now, why I am talking about this? I am talking about these that if electrons fall to a particular orbit, say n equals to 1, irrespective of from which orbit they fall, they always are of some particular frequency. And that frequency, in this case, if they fall on first orbit from any higher orbit, the frequency range is in ultraviolet and it is called Lyman series. Means frequency is in a particular range. Frequency cannot be in a different range. I am talking about only hydrogen atom at the moment. So what Bohr said that if the energy transition, state transition, electron transition is from any higher orbit to a particular orbit, in this case first orbit, then energy will be constant. If second orbit, then energy will be constant. If third orbit, energy will be constant, because he said the energies of all these levels are constant. So here E1, E2, E3, E4, E5, E6, E7, etc. What according to this diagram is, this diagram shape says that here E2 minus E1 if electron falls from second to first, E3 minus E1 energy, E4 minus E1, and so on. All these energies have some frequencies, and those frequencies fall in a specific range. And because the range was identified by Lyman, these are called Lyman series. If the electron falls from any higher orbit to second orbit, this one, then they have the frequency range in visible region. So that's why if you see, these are shown as colored. This is known as Balmer series. Why Balmer series? Because it was identified by Balmer, scientist Balmer, that irrespective of from where they fall, from any higher orbit, if the electron falls on second orbit, then the energy released is in visible region. And this is the region that we can see the objects. Due to this transition, we can see the objects. All objects, whatever we are seeing, those are visible just due to transition of electrons in visible region. The energy is emitted in visible region. That's what we are able to see. Similarly, if it is on the third orbit, it is known as Paschen series and it is infrared. Okay. If it is fourth orbit, the electrons fall on fourth orbit from any higher orbit. It is known as bracket series. And if it is n equals to 5, then it is Pfund series. All these three, that is Paschen, bracket, and Pfund series, all these are in infrared region. Paschen, bracket, and Pfund, all are in infrared region of frequency. From here, questions appear. You just need to memorize these things. Lyman series means the electron is falling on first orbit. Balmer series, second orbit. Paschen, third. Bracket, fourth. Pfund, fifth. Okay. Lyman series, the radiations are in ultraviolet region. Balmer series in visible region. All other three infrared region. IR, infrared region. Simple questions appear from here. Okay. So this is what I talked about if I represent it diagrammatically. If from any higher state it falls on n equals to 1, it is Lyman series. If n equals to 2, Balmer series, 3, Paschen series, 4, bracket series, 5, Pfund series.